probably seen a little bit of me by now, maybe. Author of Quantumology and the founder of the Quantumology group on Facebook, and the websites .net and .org, so you can investigate any of those, and please feel free to do so. Right, this is the conclusion of this 6-part series, and we studied during the last 5 weeks quarks. First of all, looked at what they are, how they're constructed, how they move from one thing to another, change flavour, they change colour by means of the gluon, which is a gauge boson. Then we went on to look at photons. So here is the electromagnetic field that we talked about in that particular talk, and that's the slice we can see, visible light. So this is all we see of photons in the normal state of affairs, but there is so much more to the photon. It's basically nothing happens in the universe without the photons say so. We talked in this episode as well about the multiverse and how that is sliced into brains, like a little bit like slices of toast in the analogies that the scientists would give you. Can't imagine for a minute that parallel universes exist in the neat filing cabinet of universes. It just doesn't work in my heart, I'm afraid. Okay, so that was the photon. And then we looked at the electron. Every atom is surrounded by electrons. We touch only electrons, essentially, if you think about it, because the atoms that are at the ends of our fingers and the atoms that are in the object that we're touching are surrounded by electrons over the nucleus, so we can never touch the nucleus, we can only actually touch electron to electron. So these are really interesting things. Then we looked at the neutrino, and this is the last particle that we looked at. It's a little neutral one in Italian, and it comes in 3 flavours. You've got the electron neutrino, the muon neutrino, and the tau, which is the gargantuan one when you look at normal mass order. So in our universe it's gargantuan. If it's an inverted mass, then it's the lightest, which throws a little bit of a spanner in the works. This is oscillation, very, very important to all the fundamental principles that we're going to talk about. So oscillation is in there as a representation of what the neutrino predominantly does. It changes flavour from one to the other as it flies. We rounded off in week 5 with the 4 forces. So you've got the strong and the weak force, which exist and function at the minuscule, microscopically quantum levels. They're the binding forces and the force that allows for all these. So these two operate at the micro level. These two, on the other hand, are completely opposite. So the electromagnetic force and gravity, they are both potentially infinite. Opposite end of the scale. So these forces also exist, therefore, in pairs. And it's quite amazing how much you find when you dig into quantum mechanics and you look at the scientific papers, how much of it as a construct falls into a pairing format. We also touched on the Higgs field, and touching on the Higgs field is realizing that as it's alone, as a scalar boson, the Higgs boson really did possibly warrant its almost worshipped status as the God particle. Coming up with it as a God particle was the anathema of most physicists. Very uncool. As a scalar boson, it would be responsible for scale, which in my book means the 3D construct of reality that we see around us, everything that we touch and see as it is. So we looked at the 4 forces in that context. And now we come to the conclusion. We've got essentially these particles here. And there's another strange pairing to come across when you just study it like this. These two, the quarks and the neutrinos, they both oscillate. They both change from one thing to another. The neutrino is oscillating as it flies, and the quark is constantly changing flavour and colour as it mixes. So these are both constantly shifting and morphing from one thing to another. These two, photons and electrons, are not. They stay pretty much as they are in terms of the model that their construction is attributed to. So here you've got the electromagnetic field. Slow radio waves at this end and gamma rays at this end, so it's changing in frequency if nothing else. And then you've got the 0 point, which is a bit of an anomaly because it's not mentioned very often in scientific papers. You don't see a lot of physicists writing stuff about the 0 point field, possibly because it's so difficult to detect, it's so difficult to get into, to find where it is, what it does, and how it does it. It is really a little bit beyond the realms of science at the moment. This is oscillation again. And this is therefore the weak force field. This is where the neutrino lives. This is the multiverse, these slices of toast here, the brains that we talked about a moment ago. Okay, so what is reality? Okay. There are lots of theories about what reality actually is. They come under various styles, really. One is the matrix. The matrix theories go into all sorts of lattice potentials, crystalline lattice potentials, mathematical lattices, all kinds of things that the word matrix could apply to. So it's not just sci-fi. A bit more sci-fi maybe is the holographic universe. And if you need more explanation on a holographic universe, there's lots of information out there, and you can also watch Star Trek The Next Generation, because of course they've got holographic in it. Another potential that's being put forward is a little bit like this, but slightly more complicated, is the simulated version of reality, which again suggests that there is some kind of third-party element to the construct of the reality that we experience. To my mind, the question really is answered by one thing. Reality has got to be physics. We've got to be able to pull together from physics the answers to how reality is truly constructed. But it's not going to be really good enough or go far enough, to my mind, to rely on the standard model as it stands. Because as it stands, it doesn't take enough account of the behaviour of these particles that it defines and puts into the boxes. It doesn't go far enough into their interaction with each other. And it certainly isn't asking anything about the question of whether consciousness itself is an element or a factor in what happens on a universal scale. So because these questions are not yet answered or open to investigation even in the fullest sense of the word, my feeling is that they have to be. And in order for that to happen, you've got to put another word in front of this. And that other word is this one. Meta. You put meta in front of physics, and you've got metaphysics. Now that's the bridge, really, between all these questions that everybody out there who isn't a physicist is busily asking of themselves and trying to find the answers to, and all the people who are physicists, and particularly leaning towards the traditional or classical ways of thinking, are not going to look at that side of the fence. They're not interested in anything that could be construed as what they call woo. And yeah, that really is a word. Second question. How much is a quanta? Well, quantum particles generally, if they've got charge, they're measured in electron volts. And of course there are lots of different measurements of electron volts, and they come in various sizes. There's MeV, which in my language is massive electron volts, and then there's GeV, which is in my language again gargantuan electron volts. So that's the measurement of charge. Doesn't really do a lot for the scale, the size of these things, because they are far too small to be quantized in size. But if you go into an Italian shop in Italy and you say Quanta, you're literally asking how much something is. And quantum is the plural of quanta. Okay, so that's one way of measuring the quanta in the quantum field. There are other ways. There's the Gaussian measurements. They're mainly mathematical. In fact, they're all mathematical, really. Way above my head, but certainly relevant to the argument. And then there's the Planck scale, which is as far as we can go down into the microscopic measurement side of things. Is it useful? Who knows? It's very, very difficult to pin anything down. So you've also got something else to consider in the mix, which I'm going to put in black here. In black. Uncertainty. The uncertainty principle is something that you must have a look at. It's very, very important. Don't let anybody tell you, by the way, that it is only to do with not being able to measure the position and the speed of something at the same time. There's way, way more to the uncertainty principle than that. So you know, look it up as much as you can, do some research, but don't let anybody kid you that it's just a case of not being able to measure two things at once. No. So the final question then in this conclusion, do we oscillate? I'm asking this question because I have considered it myself over the years, very, very deeply. It seems to me as I go through the course of my life that I go up and down in mood. Not exactly bipolar, maybe, but I've had a few labels thrown at me over the years. So we change from one thing to another. We change our circumstances. We change our relationships. We change the way those relationships work. We change the way we do things. We change our habits. We change lots and lots of things in our lives all the time. Can this be construed as oscillation? To my mind, we are what we're made of. It's a big question, this one. So, yes or no, who knows? I'm going to put another question mark under it. Because it's one of those things that right now is a bit of an unknown. It's down to definition at the end of the day. So, next time, I hope you like my Heath Robinson flip chart arrangement. Next time in Series 2, I'm going to be looking at the quantum principles. So that's when we study things like wave-particle duality, complementarity, the uncertainty principle, entanglement, and symmetry and violation, which is much loved, adored, and at the same time loathed and hated by physicists all over the world. Any of these things that you want to go ahead and look up in advance, please do. That's the whole point. Bring things to the discussion. If you want to actually be part of the live discussions, then join the Quantumology group on Facebook. And we will then conclude Series 2 and see where the discussions go from there. So thank you very much for joining me today, and I hope I see you again very soon. Take care. Bye.